2025 A-Level Combined Mathematics Paper 1, Part B, Question number 13, Part A. Part B and C of this same question will be discussed in future videos. Part A of this question has to do with matrices. This question says, let the matrix capital A be equal to this matrix here, which is 2A, 3, 1, and the matrix capital B be given by this matrix here, which is 2, 1A, 1, 4, 1, and the matrix capital C be given by this whole thing here, 4 plus A, 7, 6, 7, 3A, 4, where A is some element of the real numbers. So here, this value A, here, and here is some real constant. Now given this, we are asked to first find the values of A such that A inverse matrix exists. We're then asked to find the product of the matrices A and B in terms of simple A. Now note, it is important what the order of the multiplication here is. Here we are first multiplying A by B. So A first, then B. And then we are asked to determine the value of A such that B transpose matrix times A transpose matrix is equal to C matrix. Now given this value of A, we are asked to, for this value of A, show that capital A matrix minus capital A inverse matrix is equal to 3i, where I is the identity matrix of order 2, which is the matrix 1, 0, 0, 1. Now to start solving this question, what we're going to do is to go to the first thing where we are asked to find the values of A such that A inverse exists. So for a matrix A inverse to exist, the original matrix A needs to have two conditions. First off, it needs to be a square matrix. Now in the case of A, we can see that A is a 2 by 2 matrix, which means it's a square matrix, meaning that A inverse could exist. The second condition, given that we have a square matrix, is that the determinant corresponding to that square matrix is not equal to 0. Because if it is equal to 0, then A inverse doesn't exist. So we can say A is a square matrix. Now given that A is a square matrix, the condition that we need is that if A inverse exists, we definitely need the condition that the determinant of A, which I'm going to call det A, is not equal to 0. So not equals 0. Now this is sometimes referred to as det A like this, with like the modulus symbols on the side of it, but I personally like this notation as it makes it clear that we're talking about the determinant of a matrix. So A inverse matrix exists if and only if det A is not equal to 0, because in this case A is a square matrix already. So now what we need to do is to find det A, the determinant of the matrix A, and see if it's equal to 0, see when it's not equal to 0, and for those values of A, we can say that the A inverse matrix exists. So in this case, for a 2 by 2 matrix, the determinant of that matrix is the first value multiplied by the last value minus this value multiplied by this value. So therefore, for this particular value, det A, the determinant of A is equal to, in this case, 2 times 1, so 2 times 1, minus the other product, which is A times 3. So I'm going to write 3 times A. 3 times A. So therefore, the determinant of the matrix A is equal to 2 minus 3 times simple A. Now, in order for this to not be equal to 0, we need that 2 minus 3A equals 0 implies that 2 is equal to 3A, which implies that A is equal to 2 over 3. So therefore, we can say that A should not be equal to 3 or 2 over 3. Therefore, A inverse exists if and only if A is not equal to that value which gives us 0, which is 2 over 3. So therefore, the A inverse matrix exists if and only if A is not equal to 2/3. So we can say that A can be any element of the real numbers except for 2/3, because if A is equal to 2/3, the determinant of capital A is equal to 0, in which case we have a problem where we don't have an inverse matrix. So now with that, we've solved the first part of the question. The second part of the question is asking us to find matrix A times matrix B in terms of simple A. Now if we just write this out, matrix A times matrix B is equal to, if we multiply the two matrices, if I just draw the brackets and multiply, the first matrix is 2A, 3, 1, so we have 2A, 3, 1. The second matrix is 2, 1A, 1, 4, 1, so we have 2, 1A, 1, 4, 1. Now as we know, when we multiply two matrices like this, the two matrices need to be multiplyable. Now in this case, these two matrices are multiplyable since the number of columns here, 1, 2, is equal to number of rows in the second matrix, which is 1, 2. So now that we have that, we can multiply the two, and the resulting matrix is going to have this many number of rows and this many number of columns. So we're going to have a 2 by 3 matrix. Now if we start filling this in, as we know from the matrix multiplication algorithm, the first entry here is going to be 2 times 2, which is 4, plus A times 1, so plus A. The second entry is going to be over here, it's going to be 2 times 1 plus A times 4, so it's going to be 2 plus 4A. The last matrix entry is going to be 2 times A plus A times 1. So 2 times A plus A times 1 is going to be 3A, so we have 3A here. For the next row down here, we're going to do this thing and this thing, this thing and this thing, and this thing and this thing. So down here, for the next entry, we're going to have 3 times 2 and 1 times 1. So it's going to be 6 plus 1, which is going to be 7. For the next entry, we're going to have 3 times 1 plus 1 times 4, which is again going to be 7. And for the last entry, we're going to have 3 times A and 1 times 1, which is going to be 3A plus 1. So therefore, this entry is 3A plus 1. So therefore, A matrix times B matrix is going to be this matrix right here. Now if we consider the next part of the question, after finding AB in terms of simple A, we then need to determine the value of simple A such that B transpose times A transpose is equal to C matrix. Now, in this case, we need to know an important identity. We need to know that B transpose times A transpose is equal to A times B transpose. This is called the reversibility rule. Now, you can go ahead and try to prove this, but we don't need to prove it here. We can just use it as it is. So in this case, if we use it, we can see that, therefore, if we have the condition that B transpose times A transpose is equal to C, then that means that A times B whole thing transpose must be equal to C. Now, if we take A times B, we already know it since we just proved it. So we can substitute that directly into here, we can transpose it and then equate it to C, and then using that, we can then derive some equations which will allow us to find the exact values of A. So given this, if we substitute, if we say substituting, we get for 8B transpose, we get all of this stuff here, which I'm actually going to just copy paste. I'm going to copy this down and I'm going to put transpose on it. So we have this thing, transpose is equal to C matrix, which if you go up, C matrix is all of this stuff here, 4 plus A, 7, 6, 7, 3A, 4. So we're going to write 4 plus A, 7, 6, 7, 3A and 4. So we had this. Now if we transpose the first matrix, that means we take any index here, we take its row number, its column number, so we swap the two and we put them into a matrix. If we have a 2 by 3, it's going to turn into a 3 by 2. So this 3 by 2 matrix is equal to this other 3 by 2 matrix, which is 4 plus A, 7, 6, 7, 3A and 4. And if we transpose, 4 plus A is in the 1, 1 position, which means it stays at the 1, 1 position, so 4 plus A. This thing is in the row number 1, column number 2 position, so it becomes column number 1, row number 2, which is going to be here. So we have 2 plus 4A there. This thing goes here, this thing goes here, and then this 3A goes here, and finally this 3A plus 1 goes here. So 3A plus 1 goes here. Now, we can see that this matrix on the left, this 3 row by 2 column matrix must be equal to this 3 row by 2 column matrix. Now, for these two matrices to be equal, each of these entries must also be equal. So this 4 plus A must equal this 4 plus A, which it is. This 7 must equal this 7, which it is. This 2 plus 4A must be equal to 6, which we can use to find A. This 7 must be equal to 7, which it is. This 3A must be equal to 3A, which it is. And this 3A plus 1 must be equal to 4, which we can use to find A. So we can see that if these two matrices are equal, it must mean that 2 plus 4A is equal to 6. And additionally, it also means that 3A plus 1 is equal to 4. Now we could use either of these, and we should probably solve both of them, because if we solve both of them we should get the same answer, and if we don't get the same answer then we can have a contradiction. Now as of right now, we have not gotten any matrix questions that have contradictions in them, so we could, but it's very unlikely that we do, but still I'd recommend that you check. So for the first equation, if we solve it, we can see that 4 is equal to 4, and then divide by 4, a is equal to 1. For the second equation, we can see 3a plus 1 is equal to 4, meaning that 3a is equal to 3, meaning that a is equal to 1. So the two agree. The two agree with each other. We don't have a contradiction, and all other elements are also equal. 4 plus a is equal to 4 plus a, 7 is equal to 7, 7 is equal to 7, 3a is equal to 3a. So we have no problems in that front as well. So now we can see that a must be equal to 3. So now, if we go up and we consider what they've asked us to do, they've asked us to then, after finding the value of a, for this value of a, show that A matrix minus A inverse matrix is equal to 3 times the identity matrix. So now for this, we need to first find A inverse, since we didn't currently find A inverse. So we can say for A equals 1, we can find the matrix A, and we can also find the inverse matrix A inverse. So for A, the A matrix is simply going to be here 2A 3 1. So A is going to be equal to 1, so it's going to be 2 1 3 1. So therefore the A matrix is going to be 2 2 1 3 1. Now as for the A inverse matrix is going to be, for a 2 by 2 matrix, 1 over det A multiplied by the matrix, which is going to be basically this matrix's entries, but we swap these two and we make these two negative. So if we do that, we can see that the matrix we're going to get is 1 2 and then negative 3 negative 1. And if we replace det A as we found above was equal to 2 minus 3 times A, which in the case of A equals 1 is going to be 2 minus 3. So I'm going to write down here, divide by 2 minus 3. Or if you want, you could write that in the next step. You could first, you could take this down onto the next line, and then you could say this A inverse matrix is equal to 1 over det A multiplied by the matrix, which is 1, negative 3, 2, and then you could substitute if you want. It's your preference. I personally don't see any issue with just writing the answer directly instead of having this part over here, but you do you. So now that we have this, if we simplify this, we can see that A inverse is equal to, here we have just 1 over negative 1, which is going to be negative 1, multiplied by this matrix, which is all of the entries multiplied by negative 1, which is going to be negative 1, 1, this is going to become positive 3, this is going to become negative 2, so minus 2. Now finally, if we take this value of the A matrix and the A inverse matrix, and we do what the question asked, which was to consider A minus A inverse, we're going to get the matrix of A, which is going to be 2, 1, 3, 1. We're going to subtract from it the other matrix, which is negative 1, 1, 3, negative 2. Now if you subtract, you can get a 2 by 2 matrix, and the entries of this 2 by 2 matrix are going to be 2 minus negative 1, which is 3, 1 minus 1, which is going to be 0, 3 minus 3, which is going to be 0, and 1 minus negative 2, which is going to be 3. Now if we factor out a 3 from this, we have 3 times 1, 0, 0, 1. And this matrix here, 1, 0, 0, 1, is the identity matrix for a 2 by 2 matrix. And therefore, as we defined above, this is going to be equal to 3 times capital I, which is what we wanted to solve, where capital I is the 2 by 2 identity matrix. So as the question defined, I is the identity matrix of order 2. So now that we've done that, we've solved all of the questions in this problem. So now, let's go over finally the marks involved with each of these questions. For the first part, when you say that A is a square matrix and therefore A inverse exists, if and only if the determinant is not equal to 0, you're going to get 5 marks. When you then use that property to go down and say that A inverse exists if A is not equal to 2/3, you get another 5 marks. When you then do A times B and you finally get this answer here, when you do the matrix multiplication properly, you're going to get 10 marks. And then after that, when you are doing the B transpose times A transpose, when you use this identity here, that B transpose times A transpose is equal to A times B whole thing transposed, you're going to get a 10 marks just for that. Now, when you substitute into this down here and you get to this point, where you have one matrix that has 3 rows and 2 columns being equal to the other matrix C, which has 3 rows and 2 columns, you're going to get 5 points. And when you use this to find that A is equal to 1 and you confirm it, you get another 5 points. And finally, when you go down here and for the value of A equals 1, when you substitute all of this and you find A inverse, you get 10 marks. And finally, when you do all of this, when you do A matrix minus A inverse matrix, when you simplify this point where you have 3, 0, 0, 3, you're going to get 5 marks. And when you then equate that to 3 times the identity matrix, noticing that you can factor out a 3, you get another 5 marks. So that's all the marks for this question. I hope you enjoyed. If you have any feedback, post it in the comments down below. Thank you for watching and goodbye.